Our third speaker is Associate Professor Marnie Forster. Marnie runs the Argon Lab at ANU with the help of Agnes the robot, the first Argon robot who was designed by Marnie herself. Together, Marnie and Agnes offer a facility unmatched in its capabilities to obtain detailed age spectra that allow the recognition of different diffusion domains and enables quantitative modelling of age spectrum morphology. We will hear about how these capabilities have contributed to the characterisation of Delamerian-aged deformation and exhumation histories. Thanks, Marnie.
Thank you. I just want to thank GSSA and Tom Wise for giving me the opportunity to do this research and to come and present this today, and that I'm doing this, I'm a member of the MinEx CRC, so I'm doing it through MinEx CRC. And just a bit of blurb about Argon, and it's a really diverse geochronometer, and of course I'm not biased at all. I think it's quite amazing. And for example, we can date potassium rocks with potassium weight percent as low as 0.1%. So we can actually, you know, I mean basalts are 0.1%, but I'd never date any basalts. And we can date all varying sorts of geological scenarios like different alteration zones and granites and metasediments and all sorts of things that you can think of. So what we actually do at our lab is geochronology and thermochronology, and the geochronology, which you would assume is just a date, is more than just a date because the Argon system is affected by heat, and so it can be partially reset within a rock, within a grain, and so you can actually retain older ages within a grain as well as new younger ages when the Argon system's been reset. So it's quite common that you actually get more than one age out of a grain. Likewise, the thermochronology that we do, we do diffusion experiments, and so with our thermochronology, we get all the diffusion data. So what I'm going to show you today is what we do with that diffusion data and what we can get out of it that you can't get out of a normal geochron. So the map was provided by Tom, and he's given us, he gave me the samples that he wanted done, and there's 17 of them altogether, which of course I won't be showing you today. I'll just show you a few of them with a bit of an overview. And he's also given me a few uranium, lead and rubidium, strontium to go with it. One of the key aspects that I'll talk about shortly is that the strength that you can get out of dating two different minerals from the one rock, and how that you can actually hone in on the details and produce a temperature time plot from multiple minerals. Okay, oh, I can't actually read it, all right. So the methodology. So this is an example of where we have two ages. For example, we have about 504 and we have 494. These are actually what the community likes to call inverted, because the older age came out first, and I'll talk about that in a minute. But the spectrum rises from about 0.42 GA up to about 0.5 GA, and then it drops back to 0.49 GA. And these are sometimes not accepted to be real, but these estimates are statistically distinct, and they've actually got different diffusion parameters, and they're quite real. So the morphology of the spectra is actually really important for us. One of the things that we can do with our software is, so what we do is we define what we see to be the different ages from the diffusion data, and we push that into the software, so it's registered in the software. And so then we can do synoptic plots where we can include all the software at once, and what happens is we can then produce from that frequently measured ages, and those frequently measured ages are straight from the mass spectrometer. They are real data, they're not something just done with Excel or what have you. It's real Argon data. So then, oh, I think I'll talk about that later. Oh, what am I doing? Did I just skip one? Oh no. Okay, so if we go back to that again, so one of the things that I was talking about with Adrian today is we do need to actually get some geological context for these. So we get our frequently measured ages, but it's great to have geological context both regionally and at the microscale, because at the microscale we can start to see really what's going on. Microprobing also is great because you can start to see that the heterogeneity within the grain and a variation in the composition. So what do we do from here? Well, we actually start doing quantitative modelling. And so I'm sort of leaving out a few steps here because there's quite a few steps and I don't want to go through it, but what happens is we put the real diffusion data into the software. We have here, for example, the blue one is the real data that comes off the grain. So when we run the grain in the mass spectrometer, that blue-purple one is the real data. And then we put the diffusion data into our software, and the software actually produces a simulated spectra. And you can see here this red one is a simulated spectra. And from being able to put that into the software, then we can start to play with it, because we've got the diffusion data in there and now we can see what it does and what it all means. And for example, in this case here, what we have is we have fine grains which are older and we have coarse grains which were younger. And when we plot them up with the diffusivity and the activation energy, we can see that the activation energy is the same for all grains, but they have a different volume. And so what happens is that the older sample, which is the smaller, finer grain, is diffusing first, and it's not contamination, it's a real event, and then the younger one will diffuse later. And from that, so what will happen is that all of that data that gets put into the software, it then is told to go and find the best fit for a temperature time path, and off it goes and it produces a temperature time path. And for example, this sample, which is D5 and it's a micaceous schist, it's dominantly white mica, it's produced this time path. And it does that on its own. You know, we don't do anything, it's from the data. And so, so you can see that, oh, I knew I'd do that. You can see that we've got a growth event happening, and it represents about 70% of the gas that came out of the experiment. So if we have a play with that and we talk to the geologist who knows about the context or what have you, we can actually have a look at how that fits in with the regional geology. And for an example here, we could say that we had detrital white mica and that we had a maximum age deposit here, and then we had the revised temperature time path with new growth of white mica about here, and you can see the influence of that new growth, which took up about 70% of the experiment. I just wanted to show you a little bit of some of the other samples. For example, these are the biotite, and biotite can either be fantastic or it can be absolutely horrid. So I included them all here so that you can have a look. And you can see that, so the experiment starts here. It's really cold at about 450 degrees in the mass spectrometer, and then it works its way along. Every one of these is an increase in temperature, and that we do that so that we can gradually degas the sample. And we only do them in small steps so that we have a nice even degassing, and so we don't jump, because as soon as you jump, you're going to mix gases from different domains, and we don't want to do that because we want to see what the distinct domains are. So we have a range in here. When you pull these out individually, you'll be able to get more information, but we just thought we'd put them into a synoptic plot so that you can see the range of what the biotites were. Likewise, there were two samples which very surprisingly came out with these two very unusual and impossible spectra. So you know that there's something like XX argon, or as an alteration, something's gone in there, there's veins in there. But the interesting thing was that we got two of them that did the same thing, and they actually came out with ages, which I know this age very well from New Zealand, and another age which is known, and then the Delamerian-aged somewhere in the middle. So, you know, they didn't work, but they're still interesting. And the Gaussian plot, or the frequently measured age, is statistically done beside it. We did that as well for the K-star, so you can have a look. And normally what happens with K-star is it has very retentive domains, like big core domains we call them, and they hang on to the gas. And so you classically can have some quite old ages come out of K-star, and it's really, really common that the K-star will give you the same age as the uranium-lead, which wasn't always thought to be the case. But in these samples, for whatever reason, the K-star is young. It doesn't have any old retained ages in it, so we've got quite a few, they've got a range in there where the K-star has all come out young. Okay, so I want to just talk about, for the rest of this, doing two minerals from the one rock. For example, we can look at paleo depth, distance from source, pulses, and how hot it really gets. And I've got two examples. One of them is D8, and that's on the right-hand side of the Alawuna map at the northeast corner of the map. And it's come out with your 500 million, 500 million year age. And we decided from doing modelling on that it came out at a rapid cooling, which you can see here. This is what that means, that's rapid cooling, 500 million years. And we decided on it being 9 to 11K depth with a cryptic metasomic event at 0.47, which is this feldspar here. I want to show you a few pointers as to what traps you can fall into. So you don't go to a book or something and look up and see what's the closure temperature associated with monazite oil, and then it goes down through the line and then it gets to fission track or whatever it does, and it says this is where it fits into the thing. You just, if you're going to do a tectonic model and use that list of numbers, it's just not going to be right, because every domain inside a crystal has got its own closure temperature. And this is an example of that. For example, this was a biotite, and so if we went in and put the biotite diffusion parameters in there, we would actually get it growing at 5 to 6 kilometres depth, which is actually not possible. And even though the spectra looks as though it matches, we can put our diffusion parameters in there, when you look at reality, it doesn't work. If we put the Flogopart in, which has got much higher activation energies, for example, almost 80, we still get the same spectra, but we start to get much more real PT models. Likewise, if we're trying to look at short pulses, what happens is the biotite, it needs ridiculously short pulses, for example, 200 years at above 200 degrees. Well, that's just impossible, so immediately that doesn't work. If we have a heat pulse that's 1,000 metres distance, then the time above 200 degrees, it still has to be less than 2,000 years. And if you have a look what that does to the spectra, it's just produces a simulation of the first 10% of the spectra, which is completely doesn't align. And so you know that this can't be a biotite, so you can't do a temperature time model with that. And just one more thing on that is distance to the heat source. So the heat source needs to be within 1,000 metres so that no change in the morphology of the spectra. All right. Where am I up to? If the heat source is from a spectra is 5 kilometres away, we will significantly see a modification. So it has to be longer to do it, and so it'll immediately have an effect on the spectra. So you can say again that you can't do your temperature time when you're modelling on a biotite. The second example that I have is from the QV samples, which was given to us for the thermal history, and it's the D09. These are much younger. I was quite surprised about these being so young, but I forgot to mention that the other ones also marry up with the uranium lead, but you can see the uranium lead on the side is 419 million years, and the biotides come in at 421. They're within error of each other, and again there's there's a late pulse. Sorry, I always lose my voice. So there's a metasomatic event which has happened in the case bar. So this one married up quite well. You can actually see that it's got quite an amazing fit. It's actually a really amazing fit. In the first 10% of the gas, you can see that the fit happens very well. So we were quite confident to be able to let the software produce this temperature time model so that we can actually work out things like we had extremely rapid cooling, and we have a pulse here, and we have the upper boundary of sensitivity envelope was at 10 to 12 kilometres paleo depth. These are actually really time consuming to do these models, but in the end, if you're trying to work out where this thing's happening in Earth and how you can relate it to other areas, it's a really good way to get that sort of data. Gordon did these, and he actually really loves doing these large-scale tectonic models. In one way, it's too big a jump for the type of model that I just showed you before, but it's, you know, you can lead through different scales with these models, and you can come to the end of these where he's got 530 to 500, the accretion phase of the Delamerian, 500, the Delamerian tectonic mode switch, and he's got a slab decapitation in there. And then he moves on to the 500 million year, which is the Delamerian tectonic mode switch, which has got an analogue example of the Java trends 20 million years from today. And then he's got the 500 to 480, which is the Delamerian extension phase, exhumation during extreme extension, ore deposits, metamorphic ore complexes, etc. And the analogue example is the Oligomycene in the Basin Range province of the Western North America. And the last one he's got at 455 is the accretion of the first continental ribbon and onset of succession of the Lachlan orogenic episodes. And that's it. Thank you.